Hello everyone. Today we will study orthogonality and Gram-Schmidt process. Before I introduce what is orthogonality, let me first of all define angle. Let V be a real inner product space, and let U and V be vectors in V. The angle theta between U and V is defined as angle theta equal to inverse cosine of the inner product of U comma V divided by the norm of U and the norm of V. That's how we define angle theta between vectors U and V. Note, the above definition for angle theta is well defined. By Cauchy-Schwarz inequality, we know that the absolute value of the inner product of U and V is less or equal to norm of U times norm of V. Based on this inequality, if I divide both sides by norm of U and norm of V, since norm of U and V, they are both passive. I can bring norm of U and V into an absolute value. That's the left side. On the right side, norm of U and V divided by itself become 1. If I divide both sides by norm of U and norm of V, it becomes 1 on the right side. Since the absolute value of this expression is less than 1, that means the value inside must be between -1 and 1. So this expression, inner product of U and V over norm of U times norm of V, is between -1 and 1. That's the same as the domain of the inverse function of cosine. We know the inverse cosine looks like this. The graph of inverse cosine looks like this. That's the graph of inverse cosine. For any value between -1 and 1, the output of the function is the angle between 0 and pi, which is angle between 0 and 180 degrees. So for any input between -1 and 1, the output of the function is the angle between 0 and 180 degrees. That's how we define angles between two vectors. Next, let me show you an example. Let A be a 3 by 3 invertible matrix. Let R2 be the inner product space generated by A, and let U and V be vectors in R2. Find the angle between U and V. Here, in order to find the angle between U and V, we must first of all compute the inner product of U and V, norm of U and norm of V. Let's compute the inner product of U and V first. Here, since R2 is the inner product space generated by A, the inner product of U and V is AU dot AV. The inner product of UV is AU dot AV. What's AU? For AU, take matrix A times vector U. Here, matrix A is 1, 2, 3, 0, 1, 1. 2, 1, 2. Write U as a column vector. 3, 2, -1. Then multiply. Take row times column. I get 3 plus 4 minus 3, which is 4. Next, row times column. 0 plus 2 minus 1, which is 1. Next, row times column, I get 6 plus 2 minus 2, which is 6. That's AU. Next, find AV. AV do the same thing. Take matrix A times vector V. Matrix A is 1, 2, 3, 0, 1, 1, 2, 1, 2. Times vector V. V is 1, 0, -1. Then take row times column. I get 1 plus 0 minus 3, that's -2. Next, row times column, I get 0 plus 0 plus -1, that's -1. Next, take row times column, I get 2 plus 0 plus -2, which is 0. That's AV. Then take dot product. AU dot AV. Here, AU is a vector 4, 1, 6. AV is a vector -2, -1, 0. Then take dot product. Multiply the corresponding entries and then add them up. I get -A minus 1 plus 0, which is -9. So the inner product of UV is -9. Next, find norm of U. Let's find norm of U square first. We know that norm of U square is the inner product of U comma U. And since R2 is the inner product space generated by A, the inner product of U comma U is AU dot AU. It's the dot product AU dot AU. And we know that here, AU is 416. AU is a vector 416. Dot 416. Then multiply. 4 times 4 is 16. 1 times 1 is 1. 6 times 6 is 36. Adding up, that's 53. So, norm of U is square root of 53. Since norm of U square is 53, norm of U by itself is square root of 53. Next, let's compute norm of V. In order to compute norm of V, let's compute norm of V square first. Norm of V square is the inner product V comma V. And since R2 is the inner product space generated by A, inner product of V comma V is AV dot AV, the dot product AV dot AV. And we know that AV is a vector -2, 1, 0. We have -2, -1, 0 dot -2, -1, 0. Then compute the dot product. -2 times -2 is 4. -1 times -1 is +1. 0 times 0 is 0. Adding up, we get 5. So norm of V squared is 5, which means norm of V by itself is square root of 5. Then, once we know the inner product of U and V, norm of U and norm of V, the angle between U and V is inverse cosine of inner product of U comma V over norm of U times norm of V. Plug in the numbers. Inner product of U comma V is -9. Norm of U is radical 53. Norm of V is radical 5. That's inverse cosine of -9 over square root of 265. Next, I use my calculator. I get 123.56 degrees. That's the angle between vectors U and V. That's the angle between vectors U and V. The angle is 123.56 degrees. Next example. Let C -2, 2 be an inner product space. Here, this symbol, C -2, 2, represents a set of all continuous functions on the interval from -2 to 2. So, let C -2, 2 be an inner product space with inner product f comma g equal to the integral from -2 to 2, f of x times g of x dx, for all f and g in C -2, 2. Next, let f equal to x squared minus x and g equal to 2s minus 1 in the vector space C negative 2, 2. Find the angle between f and g. In order to find the angle between f and g, we must first of all compute the inner product of f and g, norm of f and norm of g. Then use this formula to find the angle between two vectors. Let's compute the inner product of f comma g first. For the inner product of f comma g, use the definition here. We have integral from negative 2 to 2, f of x times g of x dx. We know that f of x here is s squared minus x. G of x is 2x minus 1 times dx. Then solve integral. We can first of all multiply everything out. If we multiply everything out, we get 2s cubed minus s squared minus 2s squared plus x dx. If we combine like terms, we get 2s cubed minus 3s squared plus x dx. Next, take antiderivative. We have 2s to the power 4 over 4 minus 3s squared, 3s cubed over 3 plus s squared over 2. Evaluate from negative 2 to 2. We can simplify each term first. First term can be rewritten as s to the power 4 over 2. Second term can be rewritten as s cubed. Third term is s squared over 2. Evaluate from negative 2 to 2. Then plug in upper and lower limit and take difference. If I plug in 2, 2 to the power 4 is 16. 16 over 2 is a. If I plug in 2 here, 2 cubed is a. If I plug in 2 here, 2 squared is 4. 4 over 2 is 2. Next, plug in negative 2. Negative 2 to the power 4 is 16. 16 over 2 is a. Next, plug in negative 2 here. Negative 2 cubed is negative a. Double negative is positive, so I get a plus a here. Next, plug in negative 2 here. Negative 2 squared is 4. 4 over 2 is 2. Altogether, we get 2 minus 18, which is negative 16. So the inner product of f comma g is negative 16. Next, let's compute norm of f. In order to compute norm of f, let's compute norm of f squared first. That'll be a little easier. Let's compute norm of f squared first, which is inner product of f comma f. So in general, compute norm of f squared is a little easier than computing norm of f directly. So norm of f squared is inner product of f comma f. By its definition, we plug in f for f, plug in f for g. That's the integral from negative 2 to 2, f of x times f of x dx. And we know that f of x is s squared minus x. Next, let's multiply everything out. If we multiply, we get x to the power 4 minus 2s cubed plus s squared dx. Next, take antiderivative. If we take antiderivative here, we get x to the power 5 over 5 minus 2s to the power 4 over 4 plus s cubed over 3. Evaluate from negative 2 to 2. If we plug in 2, 2 to the power of 5 is 32. I get 32 over 5. If I plug in 2 here, 2 to the power of 4 is 16. 16 times 2 is 32. 32 divided by 4 is A. If I plug in 2 here, 2 cubed is A. I get A over 3. Next, plug in negative 2. Negative 2 to the power of 5 is negative 32 over 5. Negative 2 to the power of 4 is 16. 16 times 2 is 32. 32 divided by 4 is A. If I plug in negative 2 here, negative 2 cubed is negative A. So I get minus A over 3. Here, negative A minus negative A, they can cancel. 32 minus negative 32 is 64. So I get 64 over 5. A minus negative A is 16. I get 16 over 3. Then add them up. In my calculator, I get 272 over 15. That's norm of f squared. So for norm of f, we take square root, which is square root of 272 over 15. That's norm of f. Next, let's compute norm of g. In order to compute norm of g, let me compute norm of g squared first. For norm of g squared, by definition of norm, that's the inner product of g comma g. Then, by the definition of this inner product here, let's integral from negative 2 to 2, g of x times g of x dx. We know that g of x is 2x minus 1. So plug in, we have integral from negative 2 to 2, 2x minus 1 times 2x minus 1 dx. Next, multiply everything out. We get 4x squared minus 4x plus 1 dx. Then take antiderivative. We get 4x cubed over 3 minus 4x squared over 2 plus x. Then evaluate from negative 2 to 2. If I plug in 2 here, I get 32 over 3 minus A plus 2. If I plug in negative 2 here, I get negative 32 over 3 minus A minus 2. Then here, negative A minus negative A get cancelled. 32 over 3 minus negative 32 over 3 is 64 over 3. 2 minus negative 2 is 4, which is 76 over 3. That's norm of g squared. So for norm of g, take square root. We get square root of 76 over 3. That's norm of g. Now, once we know the inner product of f and g, norm of f and norm of g, the angle is inverse cosine of the inner product of f comma g over norm of f times norm of g. Inner product of f comma g is negative 16. Norm of f is radical 272 over 15. Norm of g is radical 76 over 3. Then use calculator. In my calculator, I get 138.29 degrees. That's the angle between function f and g. That's the angle between functions f and g. Next, let me define orthogonality based on definition of angle. We know that for any vectors u and v, the angle between two vectors is always inverse cosine of this expression. And we know that for inverse cosine function, when the input is 0, the output is pi over 2, which is 90 degrees, which means two vectors perpendicular. If the angle between two vectors is 90 degrees, that means two vectors perpendicular. And here we can see that in this expression here, the numerator is the inner product of u comma v. So when the inner product of u comma v is 0, the input of inverse cosine function is 0, and the angle between two vectors is 90 degrees, which means two vectors perpendicular. So when the inner product of two vectors is 0, two vectors perpendicular. Based on this idea here, it makes sense to define orthogonality in the following way. Let V be a real inner product space, and let U and V be vectors in V. If the inner product of U comma V is 0, then we say U and V are orthogonal, denoted by this symbol, U orthogonal to V. Next, let me show you an example. In example 1, let W be a vector 1, 1, negative 1 in R3. Determine whether W is orthogonal to U and or W is orthogonal to V. Here, in order to determine whether W is orthogonal to U or V, we take their inner product. If the inner product of W comma U is 0, then they are orthogonal. Otherwise, they are not orthogonal. How can we find the inner product here? In example 1, there's one mistake here. It should be R3. Because each vector has 3 components. It should be R3. Now, the inner product in example 1 is defined as R3 is the inner product space generated by A, which means inner product of U comma V is AU dot AV. Inner product of U comma V is AU dot AV. And similarly here, inner product of W comma V comma U is AW dot AU. So inner product of W comma U is AW dot AU. What's AW? For AW, take matrix A times W. Here A is the matrix 1, 2, 3, 0, 1, 1, 2, 1, 2. W is the vector 1, 1, negative 1. Now let's multiply. Take row times column. I get 1 plus 2 minus 3, which is 0. Next row, I get 0 plus 1 minus 1, which is also 0. Next row, I get 2 plus 1 minus 2, that's 1. So AW is 0, 0, 1. AW is a vector 0, 0, 1. What's AU? For AU, we take A times U. In example 1, we know that AU is a vector 4, 1, 6. In example 1, we know that AU is 4, 1, 6. So AU is a vector 4, 1, 6. If we multiply, what do we get? To dot product here, 0 times 4 is 0. 0 times 1 is 0. 1 times 6 is 6. 0 plus 0 plus 6 is 6, which is not 0. If the inner product of WU is not 0, that means W and U, they are not orthogonal. So W is not orthogonal to U. W is not orthogonal to U. How about WV? Are they orthogonal? Let's find the inner product. Let's find the inner product of W comma U, W comma V. By the definition here, inner product of U comma V is AU dot AV. So So inner product of w comma v here, it should be aw dot av. The inner product of w comma v is aw dot av. What's aw? aw is 0, 0, 1. What's av? In example 1, we know that av is -2, -1, 0. Then do the dot product. We get 0 plus 0 plus 0, which is 0. If the inner product of wv is 0, that means w and v they are orthogonal. So w is orthogonal to v. Next example. Let h equal to s plus 1 in C -2, 2. Determine whether h is orthogonal to f and or h is orthogonal to g. Here, in order to determine whether h is orthogonal to f or g, we take their inner product. If the inner product of h and f is 0, then they are orthogonal. Otherwise, they are not orthogonal. Now, how can we find the inner product here? In example 2, the inner product of f comma g is defined as the integral from -2 to 2 f of x times g of x dx. So for the inner product of h comma f, we take integral from -2 to 2 h of x times f of x dx. Here, h of x is s plus 1. f of x, in example 2, f of x is s squared minus x. Plug in. Then take antiderivative. We can first of all multiply everything out. We get s cubed minus s squared plus s squared minus x dx. Cancel s squared. Let's integral from -2 to 2 s cubed minus x dx. Then take antiderivative. We get s to the power 4 over 4 minus s squared over 2. Evaluate from -2 to 2. If I plug in 2, 2 to the power 4 is 16. 16 over 4 is 4. If I plug in 2 here, 2 squared is 4. 4 over 4. 4 over 2 is 4 over 2 is 2. Next, plug in -2. -2 to the power 4 is 16. 16 over 4 is 4. If I plug in -2 here, -2 squared is 4. 4 over 2 is 2. 4 minus 2 is 2. 4 minus 2 is 2. And 2 minus 2 is 0. Since the inner product of f and g is 0, since the inner product of h and f is 0, that means h is orthogonal to f. Next, let's check inner product for h and g. If the inner product is 0, then h and g they are orthogonal. Otherwise, they are not orthogonal. By definition of inner product here, let's integral from -2 to 2 h of x times g of x dx. That's how we define inner product in example 2. And here we know that h of x is s plus 1. How about g of x? In example 2, g of x is 2x minus 1. Dx. Then multiply out. If I multiply everything out, I get 2s squared minus x plus 2x minus 1 dx. That can be rewritten as 2s squared minus x minus 1. 2s squared plus x minus 1 dx. Then take antiderivative. we get 2s cubed over 3 plus s squared over 2 minus x. Evaluate from negative 2 to 2. If we plug in 2 for x, 2 cubed is 8. 8 times 2 is 16. We get 16 over 3. If we plug in 2 for x, 2 squared is 4. 4 over 2 is 2. Minus 2. If we plug in negative 2, negative 2 cubed is negative 8. Negative 8 times 2 is negative 16. Negative 2 squared is 4. 4 over 2 is 2. If I plug in negative 2 here, negative 2 is positive 2. So altogether, 16 over 3 minus negative 16 over 3 is 32 over 3. 2 minus 2 can cancel. 2 plus 2 is 4. Minus 4. 32 over 3 minus 4 is 20 over 3, which is not 0. Since the inner product of h and g is not 0, that means h and g, they are not orthogonal. So h and g, they are not orthogonal. Next, let me introduce orthogonal set. Let V be a real inner product space, and let S be a subset of V. If every pair of vectors in S is orthogonal, then S is called orthogonal set. Which means, if any two vectors in S is orthogonal, then S is called orthogonal set. That's how we define orthogonal set. For orthogonal set, there are two special cases. In general, if S is empty set, or it contains only one vector. If S is empty set, or it contains only one vector, in these two cases, there are no pairs of vectors, but we still consider the set as orthogonal set. In these two cases, when S is empty set, or it contains only one vector, in these two cases, there are no pairs of vectors, but we still consider the set as orthogonal set. Those are two special cases. Next, let me show you an example. Example 3. Let M22 be a real inner product space with the standard inner product in M22. In general, in an inner product space, if it doesn't specify an inner product, we consider the standard inner product. In an inner product space, if it doesn't specify an inner product, we consider the standard inner product. Let S be a set of 3 vectors. In M22, each vector is a 2 by 2 matrix. In M22, each vector is a 2 by 2 matrix. So let S be a subset of M22. Determine whether S is orthogonal set. So in order to determine whether S is orthogonal set, we try to check every pair. If every pair of vectors is orthogonal, then S is orthogonal set. Otherwise, if one pair of the vectors they are not orthogonal, then S is not orthogonal set. So if every pair of vectors in S is orthogonal, then S is orthogonal set. Otherwise, if one pair of the vectors is not orthogonal, then S is not orthogonal set. So let's verify each pairs. Let me first of all call the first matrix A. Call the second matrix B. And call the third matrix C. In order to verify whether A and B are orthogonal, we take their inner product, A comma B. And the standard inner product in M22. The standard inner product in M22 is the trace of A transpose times B. That's the standard That's the standard inner product M22. It's the trace of A transpose times B. For A transpose, in matrix A, write rows in columns. We have 1, 2, 3, 4. That's A transpose times B. B is the matrix 2, -5, 0, 2. Then multiply the matrices. Multiply the matrices. Take row times column. Row times column. I get 2 plus 0, which is 2. Next, take row times column. I get -5 plus 6, which is 1. Next, take row times column. I get 4 plus 0, which is 4. Next, take row times column. I get -10 plus A, which is -2. Next, find the trace of this matrix. The trace of a matrix is the sum of the main diagonal. So the sum of main diagonal here, 2 plus -2 is 0. The sum of main diagonal, 2 plus -2 is 0, which means the inner product of A comma B is 0. If the inner product of AB is 0, that means A and B they are orthogonal. Next, let's check A and C. Let's find the inner product for AC. Using the standard inner product M22, that's the trace of A transpose times C. This is the standard inner product M22. Trace of A transpose times C. For A transpose, in matrix A, we put rows in columns. We have 1, 2, 3, 4. This is matrix A. That's A transpose. Then for C, copy matrix C. Put it here. We get 1, 0, 1, -1. Then multiply. Take row times column. 1 plus 3, that's 4. Next, row times column. I get 0 plus -3. Next, row times column. I get 2 plus 4, that's 6. Next, row times column. I get 0 minus 4. Next, for trace of this matrix, we find the sum of the main diagonal. I get 4 plus -4, which is 0. Since the inner product of AC is 0, that means vectors A and C are orthogonal. So A and C, they are orthogonal to each other. Next, let's find the inner product of vectors B and C. For inner products of BC, using the standard inner product M22, we have trace of B transpose times C. That's the standard inner product M22. Trace of B transpose times C. For B transpose, in matrix B, write rows in columns. I get 2, -4 in the first column, 0, 2 in the second column. That's B transpose times C. C is 1, 0, 1, -1. Then multiply the matrix. Use row times column. Row times column. I get 2 plus 0, which is 2. Next, row times column. I get 0 plus 0, which is 0. Next, row times column. I get -5 plus 2, that's negative 3. Next, row times column, I get 0 plus negative 2. Next, find the trace of this matrix. For the trace of a matrix, we find the sum of the main diagonal. Here we get 2 plus negative 2, which is 0. If the inner product of two vectors is 0, that means these two vectors are orthogonal to each other. So B is orthogonal to C. Since every pair of vectors are orthogonal, then we say S is an orthogonal set. Therefore, S is an orthogonal set. Since every pair of vectors in S is orthogonal, we say S is an orthogonal set. Next, let me show you a theorem. Let V be a real inner product space. Let V1, V2 be vectors in V, and let K1, K2 be positive scalars. If U1 equal to K1 times V1, and U2 equal to K2 times V2, then the angle between U1, U2 is the same as the angle between V1, V2. So, a rough idea about this theorem is that suppose V1, V2 are two vectors in V. If I multiply V1, V2 by some positive scalars, either we stretch the vector V1, V2, or we may shrink the vector V1, V2, depends on what K is. If K is more than 1, we stretch the vector V1, V2. If K is less than 1, we shrink the vector V1, V2. We shrink the vector V1, V2. So by multiplying V1, V2 by some scalars, by some positive scalars, either we stretch the vectors or we shrink the vectors. Depends on what K is. If K is more than 1, we stretch the vectors. If K is less than 1, we shrink the vectors. In both cases, the angle between the vectors stays the same. In both cases, the angle between the vectors stays the same. That's what this theorem says. When we multiply V1, V2 by some positive scalars, the angle between the vectors stays the same. That's what this theorem says. Now let's prove it. How can we prove the theorem here? We try to prove that the angle between U1, U2 is the same as the angle between V1, V2. We know that the angle between U1, U2, by definition of angle, that's inverse cosine of the inner product of U1, U2 over the norm V1 times the norm V2. That's how we define angle between two vectors. Here, U1, U2 can be rewritten as KV1, KV2. So on the bottom, U1 is K1, V1. U2 is K2, V2. Next, let's simplify this expression. On the numerator, by epsilon 3 of inner product, I can pull out the scalar in front of the first vector. By epsilon 3 of inner product, I can pull out the scalar in front of the first vector. By a property of inner product, I can pull out the second scalar. By a property of inner product, I can pull out the scalar from the second vector. So I get K1 times K2 here. By epsilon 3 of inner product, I can pull out K1. By a property of inner product, I can pull out the scalar of the second vector. I pull out K2. So I get K1, K2 times the inner product of V1, V2. On the bottom, by a property of norm, K1 is a scalar, I can pull it outside. I get absolute value of K1 times norm of V1. Similarly, by a property of norm, I can pull out K2. Since K2 is a scalar, I can pull out K2. I get absolute value of K2 times norm of V2. Then let's simplify. On the top, I get K1, K2 times inner product of V1, V2. On the bottom, since K1, K2, they are positive scalars, when we take absolute value, it stays the same. So we get K1 times K2 times norm of V1 times norm of V2. Then I can cancel K1, K2 from top and the bottom. Continue here. I get inverse cosine of V1, V2, inner product of V1, V2 over norm of V1 times norm of V2. If I cancel K1, K2 from top and the bottom, that's what I get here. And here you can see that this expression matches an angle between vectors V1, V2. This expression is the same as the angle between V1 and V2. Therefore, the angle between U1 and U2 is the same as the angle between V1 and V2. So the angle between U1 and U2 is the same as the angle between V1 and V2. Let's complete the proof of this theorem. So this theorem says, for any vectors V1, V2 in V, whenever we stretch or we shrink the vectors V1 and V2, the angle between the vectors stays the same. Similarly, if V1 and V2 perpendicular to each other, if V1 and V2 are orthogonal to each other, whenever we stretch or we shrink the vectors, the angle between the vectors stays the same, which means if V1 and V2 are orthogonal, when we stretch or shrink the vectors, the resulting vector, they are still orthogonal. In addition, for orthogonality, this fact is also true when k1, k2 is 0 or negative. For example, if k1 is 0, then u1 will be 0. Then the inner product of u1, u2 will be 0, u2. And we know that the inner product of 0 vector with another vector is always 0. Since the inner product is 0, u1, u2, they are orthogonal to each other. And if k1, k2 they are negative, then u1, u2 will point to the opposite direction as v1, v2. Since v1 points upward, if k1 is negative, then u1 will point downward. Similarly, since v2 points to the right, if k2 is negative, u2 will point to the left. They are still orthogonal. So we can see that for orthogonality, this fact is also true when k is 0 or negative. So based on this, we have the following theorem. Let V be a real inner product space. Let v1, v2 be vectors in V, with v1 orthogonal to v2. If u1 equal to k1, v1, u2 equal to k2, v2, for some scalars, k1, k2. Here, k1, k2 could be any scalars. It could be positive, negative, or it could be 0. Then u1 is orthogonal to u2. So if v1 is orthogonal to v2, then by multiplying v1, v2 by any scalars, u1, u2 is also orthogonal to each other. How can we prove it? Here we try to prove u1 is orthogonal to u2. In order to prove u1 is orthogonal to u2, we try to prove that their inner product is 0. Since v1 is orthogonal to v2, then we know that the inner product of v1, v2 is 0. The inner product of u1, u2, since u1 is k1, v1, u2 is k2, v2, I get inner product of k1, u1, k2, u2. Then by epsilon 3 of inner product, I can pull out k1 from the first vector. So I get v1 here. Then next, by a property of inner product, I can pull out k2 from the second vector. So I get k1, k2 times inner product of v1, v2. Since the inner product of v1, v2 is 0, I get k1 times k2 times 0, which is 0. Therefore, since the inner product of u1, u2 is 0, we can say u1 is orthogonal to u2. So, if v1, v2 are orthogonal vectors, by multiplying v1, v2 by any scalars, the resulting vector, they are still orthogonal. Next theorem, let V be a real inner product space, and let V be a non-zero vector in V. If vector u is V over norm V, then u is a union vector. How can we prove it here? How can we prove u is a union vector? In order to prove u is a union vector, we try to show that norm of u is 1. What's norm of u here? We know that u is a vector v over norm of v. So norm of u can be written as norm of v over norm of v. Inside the norm here, v divided by norm of v can be rewritten as 1 over norm of v times vector v. That's a scalar, that's a vector. That's a scalar, that's a vector. Then, by a property of norm, I can pull out a scalar. By a property of norm, I can pull out a scalar. If I put all together, I get absolute value of 1 over norm of V times norm of V. If I put on a scalar, I add absolute value. I get absolute value of 1 over norm of V times norm of V. If I pull out this, what's left is V inside the norm. And we know that norm of V is always positive. Norm of V is always positive. Since V is a non-zero vector, norm of V is always positive. Since V is a non-zero vector, norm of V is always positive. Absolute value of a positive number stays the same. We get 1 over norm of V times norm of V. Then we cancel norm of V here. If we cancel norm of V, we get 1. Since norm of U is 1, that means U is a unit vector. That's the proof of this theorem. Note, in the above theorem, the procedure V over norm of V is called the normalization of vector V. Or we can also say it's called normalizing V. This procedure, V over norm V, is called the normalization of V, or normalizing V. It generates a unit vector in the same direction of vector V. Here, do you know why I'm adding quotation marks for the word direction? It's because in a general vector space, the direction of a vector is a very, very abstract concept. For example, in example 3, these 3 matrices, they are vectors in M22. But what's their directions? We can see that it's very, very abstract. In example 2, F and G, they are vectors in C-2, 2. But what's their directions? We can see that the direction of these 2 vectors is very, very abstract. So in general, the direction of a vector is a very, very abstract concept in a general vector space. We can only imagine the direction in our head, but we cannot draw it out. That's why we put quotation marks for the word direction. It's a very, very abstract concept. We can only imagine this direction in our head, but we cannot draw it out. Next, let me introduce Ulcer Normal Set. Let V be a real inner product space, and let S be a subset of V. If S is an orthogonal set, and every vector in S is a unit vector, then S is called Ulcer Normal Set. So Ulcer Normal Set is an orthogonal set where every vector in the set is a unit vector. That's how we define Ulcer Normal Set. And for Ulcer Normal Set, there's a special case, the NP set. In general, the NP set is considered as an Ulcer Normal Set. We know that in general, the NP set has no vectors, but we consider that's a special case. We consider the NP set as an Ulcer Normal Set. That's a very, very special case. So that's how we define Ulcer Normal Set. Next, let's look at a theorem. Let V be a real inner product space. If S equal to V1, V2, Vn is an orthogonal set in V with non-zero vectors, which means V1, V2, Vn, they are non-zeros. They are not zero vectors. Then S prime equal to V1 over norm of V1, V2 over norm of V2, and Vn over norm of Vn. S prime is an Ulcer normal set in V. How can we prove it? The proof is straightforward. We try to show that S prime is also a normal set. We try to show that this is an orthogonal set, and every vector is a unit vector. So the U1 equal to V1 over norm V1, U2 equal to V2 over norm V2, and Un equal to Vn over norm Vn. Then S prime equal to U1, U2, Un. And by the previous theorem, any vector divided by its norm is a unit vector. By the previous theorem, any vector divided by its norm is a unit vector. So by the previous theorem, U1, U2, Un, they are all unit vectors. They are all unit vectors. U1, U2, Un, they are all unit vectors. Next, we shall show that U1, U2, Un, every pair of U1, U2, Un, they are orthogonal to each other. Let Ui and Uj be two vectors in S prime with I not equal to j, which means they are different vectors. With I not equal to j, which means Ui, Uj, they are different vectors. We try to show that they are orthogonal. Here, Ui is the vector Vi over norm Vi, which can be rewritten as 1 over norm Vi times Vi. And Uj is the vector Vj over norm Vj, which can be rewritten as 1 over norm Vj times Vj. Since S is orthogonal set, that means every pair of vector in S is orthogonal. So Vi is orthogonal to Vj. Since S is orthogonal set, then Vi is orthogonal to Vj. And by earlier theorem, we know that if two vectors are orthogonal, then any scalar multiple of these two vectors is also orthogonal. If two vectors are orthogonal, then any scalar multiples of these two vectors is also orthogonal. Here, since Ui and Uj, they are scalar multiples of Vi and Vj, by the earlier theorem, these two vectors, Ui and Uj, they are also orthogonal. Since Ui and Uj, they are scalar multiples of Vi and Vj. Which means any pair of vectors in S prime is orthogonal. Since Ui and Uj is orthogonal, that means every pair of vectors in S prime is orthogonal. Therefore, S prime is a orthogonal set. Since every pair of vectors in S prime is orthogonal, S prime is an orthogonal set. And we know that every vector in S prime is a unit vector. So S prime is an Ulcer normal set. Since S prime is a orthogonal set, and every vector in S prime is a unit vector, S prime is an Ulcer normal set. That complete the proof of this theorem. Note, in the above theorem, the procedure V1 over norm V1, V2 over norm V2, and so on, Vn over norm Vn. This procedure together is called the normalization of S. Or it's also called normalizing S, normalizing set S. Next, let's create an example. In example 3, construct Ulcer normal set by normalizing S. In example 3 here, S has 3 vectors. There are vectors in M22. And we know that S is an orthogonal set. We try to construct Ulcer normal set by normalizing S, which means we take each vector in S, divide by their norm. Take each vector in S, divide by their norm. So in S, there are 3 vectors, and S is an orthogonal set. First vector is 1, 2, 3, 4. We call the first vector A. Second vector is the matrix 2, -5, 0, 2. We call the second matrix B. The third vector is the matrix 1, 0, 1, -1. We call the third vector C. We know that S is an orthogonal set. We try to normalize S, which means take each vector, divide by their norm. Let's find the norm for each vector first. How can we find the norm of matrix A? In order to compute norm of A, let's compute norm of A squared first. We know that norm of A squared is the inner product of A comma A. And in example 3, we use the standard inner product M22. In example 3 here, we use the standard inner product M22, which is the trace of A transpose times A. What's A transpose here? For A transpose in matrix A, write rows in columns, put rows in columns. We get 1, 2, 3, 4 times matrix A. 1, 2, 3, 4. Next, multiply the matrices using row times column. Row times column. 1 plus 9 is 10. Next, row times column. 2 plus 12 is 14. Next, row times column. 2 plus 12 is 14. Next, row times column. 4 plus 16 is 20. And the trace of a square matrix is the sum of the main diagonal. Here, 10 plus 20 is 30. That's the norm of A square. So for norm of A, take square root, we get square root of 30. That's norm of A. Next, let's compute norm of B. In order to find norm of B, let's compute norm of B squared first. We know that norm of B squared is inner product of B comma B. Since we are using the standard inner product in M22, that's trace of B transpose times B. That's how we define the standard inner product in M22. So for B transpose in matrix B, put rows in columns. So first column is 2, -5. Put rows in columns. Second column is 0, 2. That's B transpose. Matrix B is 2, -5, 0, 2. Then multiply. Use row times column. Row times column, we get 4 plus 0, which is 4. Row times column, I get -10 plus 0, that's -10. Row times column, I get -10. Row times column, I get 25 plus 4, that's 29. Then, for the trace of a square matrix, we add the main diagonal together. We get 4 plus 29, that's 33. That's norm of B squared. So for norm of B, we take square root. We get square root of 33. That's norm of B. Now let's find norm of C. In order to find norm of C, let's find norm of C squared first. Norm of C squared is inner product of C comma C. That's how we define norm. And we know that the standard inner product in M22 is trace of C transpose times C. For C transpose, in matrix C, put rows in columns. We get 1, 0, 1, -1. That's C transpose. C is the matrix 1, 0, 1, -1. Then multiply. Take row times column. 1 plus 1 is 2. Row times column. 0 plus -1 is -1. Next, row times column. 0 plus -1 is -1. Next, row times column. 0 plus 1 is 1. Then, for the trace of a square matrix, n entries in the main diagonal, I get 2 plus 1, which is 3. That's the norm of C squared. So for norm of C, we take square root. We get square root of 3. That's norm of A, B, and C. Next, we can normalize S. If I take matrix A divided by norm of A, that's the same as 1 over norm of A times matrix A. And we know that norm of A is square root of 30. A is the matrix 1, 2, 3, 4. Multiply. We get 1 over square root of 30, 2 over square root of 30, 3 over square root of 30, and 4 over square root of 30. That's how we normalize matrix A. That's how we normalize matrix A. Next, normalize matrix B. We use B divided by norm of B. That's the same as 1 over norm of B times B. And we know that norm of B is square root of 33. B is the matrix 2, -5, 0, 2. Then distribute. We get 2 over radical 33, -5 over radical 33, 0, and 2 over radical 33. That's how we normalize B. Next, normalize C. We take C over norm of C. That's the same as 1 over norm of C times C. And we know that norm of C is radical 3 times C. C is the matrix 1, 0, 1, -1. Then distribute. If we distribute, we get 1 over radical 3, 0, 1 over radical 3, and -1 over radical 3. That's how we normalize C. So the orthonormal normal set is, let me call the orthonormal normal set S prime. I put the normalized vector together. Put these 3 vectors together. Put these 3 normalized vectors together. I get 1 over radical 30, 2 over radical 30, 3 over radical 30, 4 over radical 30. That's the first vector. Second vector is 2 over radical 33, -5 over radical 33, 0, and 2 over radical 33. The third vector is 1 over radical 3, 0, 1 over radical 3, -1 over radical 3. That's how we normalize S. This is an orthonormal normal set. Next, let me show you a theorem. Let V be a real inner product space, and the S equal to V1, V2, Vn be a subset of V. If S is an orthogonal set with non-zero vectors, then S is linearly independent. So this theorem says an orthogonal set with non-zero vectors is always linearly independent. How can we prove it? For this theorem, try to prove that S is linearly independent. So I first of all set K1 V1 plus K2 V2 plus Kn Vn equal to 0. If I can prove that K1, K2, Kn they are all zeros, that means V1, V2, Vn they are linearly independent. But here, how can we show that K1, K2, Kn they are all zeros? In order to show K1, K2, Kn they are all zeros, we try to apply inner product. Here, for inner product, we think of inner product as multiplication, as a product, as a multiplication. If I multiply both sides by V1 using inner product, then how it looks like? If I multiply both sides by V1 using inner product, how it looks like? If I multiply both sides by V1, on the left side, I get K1 V1 plus K2 V2 plus Kn Vn, comma V1. Here I multiply left side by V1 using inner product. If I multiply right side by V1 using inner product, I get 0, comma V1. So I multiply left side by V1 using inner product, and I multiply right side by V1 using inner product. Next, let me simplify both sides. How can we simplify left side? In the left side, for the first vector here, there are n terms. By the second LCM of inner product, if there are multiple terms in the first vector, I can distribute the second vector into the first vector. That's the second LCM of inner product. So since in the first vector there are multiple terms, I can distribute second vector into the first vector. So I get K1 V1 comma V1 plus K2 plus K2 V2 comma V1 plus Kn Vn comma V1. That's the left side. I distribute V1 to each term in the first vector. Now what's the right side? What's the inner product of 0, comma V1? By one of the properties of inner product, inner product of 0, comma any vector is 0. Inner product of 0 with any vectors is always 0. So inner product of 0, comma V1 is 0. Now, keep simplifying left side. By the third LCM of inner product, if there's a scalar in front of the first vector, I can put it outside. If there's a scalar in front of the first vector, I can put the scalar outside inner product. So, if there's a scalar in front of the first vector, I can put it outside inner product. I get K1 V1 comma V1 plus K2 comma K2 times inner product of V2 comma V1. I pull out K2. Next, I can pull out Kn. If I pull out Kn, I get Kn times the inner product of Vn comma V1 equal to 0. Here we know that the inner product of V1 comma V1, that's norm of V1 squared. Then how about the inner product of V2 comma V1, V3 comma V1, and Vn comma V1? Since S is orthogonal set, that means every pair of vectors in S are orthogonal, which means their inner product must be 0. So the inner product of V2 comma V1 must be 0. V3 comma V1 must also be 0. And Vn comma V1 is also 0. Since they are orthogonal vectors, their inner product must be 0. So here, since S is orthogonal set, then the inner product of V2 comma V1 is 0. V3 comma V1 is also 0. And Vn comma V1 is also 0. Hence, we have K1 times norm V1 squared. Inner product of V1 comma V1 is norm V1 squared plus K2 times 0. since inner product of v2, v1 is 0. And similarly, the rest are all zeros. Inner product of vn, v1 is 0. They're equal to 0. Since they are all zeros, the rest are all zeros. We have k1 times norm of v1 squared equal to 0. Also, since v1, v2, vn, they are non-zero vectors, we know that v1 is not 0. Since v1 is not 0, then norm of v1 is not 0. Hence, norm of v1 squared is not 0. If two scalars multiply to be 0, and we know one of them is not 0, then the other one must be 0. Therefore, k1 must be 0. Next, similarly, if I multiply for the same equation, if I multiply both sides by v2 using inner product, we can show that k2 is 0. If I multiply both sides by v2 using inner product, I can show that k2 is 0. If I multiply both sides by v3 using inner product, I can show that k3 is 0. And continuously, if I multiply both sides by vn using inner product, I can show that kn is 0. Since k1, k2, k3, kn, they are all zeros, that means the vectors v1, v2, vn, they are linearly independent. Is v1, v2, vn, they are linearly independent. So S is linearly independent. Let's complete the proof. Let's complete the proof of this theorem. Any orthogonal set with non-zero vectors is always linearly independent. Next, based on this theorem, we have the following corollary, which says let V be a real inner product space with dimension of V equal to n. If S is a orthogonal set in V with n non-zero vectors, then S is a basis in V. The proof of this corollary is very simple. Let me prove it here. Since S is a orthogonal set with non-zero vectors, since S is a orthogonal set with non-zero vectors, then by the previous theorem, S is linearly independent. By the previous theorem, S is linearly independent. Since S is a linearly independent set, in V, with m vectors, and dimension of V is n. Since S is a linear independent set in V with n vectors, and dimension of V is n, then S spans V. Hence, S is a basis in V. Let's complete the proof. So, if S is a orthogonal set in V with n non-zero vectors, then S is a basis in V, assuming the dimension of V is n. So that's the proof of this corollary. Next, based on the above corollary, let me introduce some terminologies. Note, if for a orthogonal set form a basis in V, then it's called a orthogonal basis in V. If a orthogonal set form a basis in V, then it's called orthogonal basis in V. So this set S here is an orthogonal set, and if form a basis in V, this set S here is called orthogonal basis in V. Similarly, if an Ulcer normal set form a basis in V, then it's called Ulcer normal basis in V. If an Ulcer normal set form a basis in V, then it's called Ulcer normal basis in V. Next, let me show how to construct an orthogonal and an Ulcer normal basis, which is called the Gram-Schmidt process, which is the construction of an orthogonal basis. Let V be a real inner product space, and let S be the set of U1, U2, Un. Let S be a basis in V. The following procedures will construct an orthogonal basis of V based on S. Step 1. Let V1 equal to U1. That's first step. Let U1 equal to V1. Step 2. Let V2 equal to U2 minus the inner product of U2 comma V1 over the norm V1 squared times V1. Remember, this is an orthogonal projection of U2 on V1. This is an orthogonal projection of U2 on V1. Step 2, let V2 equal to U2 minus the orthogonal projection of U2 on V1. This will construct a vector orthogonal to V1. We can check. We can check their inner product. Here, if I take inner product of V2 comma V1, V2 is this expression here. I get U2 minus inner product of U2 comma V1 over the norm of V1 square times V1 comma V1. I first of all replace V2 with this expression. With this expression. Leave V1 the same. Next, simplify. By the second axiom of inner product, I can distribute V1 to both of them. I get U2 comma V1 minus U2 comma V1 over the norm of V1 square times V1 comma V1. Here, by the second axiom of inner product, I distribute V1 to both vectors. That's the first vector, that's the second vector. Distribute V1 to both vectors. I get this. Then I leave the first inner product the same. I get U2 comma V1. For the second inner product, that's a coefficient, that's a scalar in front of the vector. Then by the third axiom of inner product, I can pull out this scalar. So pull the scalar out of the inner product. I have U2 comma V1 over the norm of V1 square. Pull this outside. What's left is V1 comma V1. Pull this outside. What's left is V1 comma V1. I leave the first inner product the same. For the second term here, the top stays the same. Bottom stays the same. Inner product of V1 comma V1, that's the norm of V1 square. This is exactly the same as the denominator. Make it cancel. What's left is U2 comma V1 minus U2 comma V1. This then looks exactly the same. Make it cancel. So we get 0. So V2 comma V1, the inner product of V2 comma V1 is 0. That means V2 is orthogonal to V1. So by this construction here, V2 is orthogonal to V1. Step 3. Let V3 be U3 minus the inner product of U3 comma V1 over norm of V1 square times V1 minus the inner product of U3 comma V2 over the norm of V2 square times V2. And here, this is an orthogonal projection of U3 on V1. This is an orthogonal projection of U3 on V1. And this is an orthogonal projection of U3 on V2. This is orthogonal projection of U3 on V1. And this is orthogonal projection of U3 on V2. So for V3, I take U3 minus orthogonal projection of U3 on V1 minus orthogonal projection of U3 on V2. Then this vector, V3, will be orthogonal to both V1 and V2. We can check. If we take V3, inner product of V3 comma V1, I replace V3 with this expression. I get U3 minus inner product of U3 comma V1 over norm of V1 square times V1 minus the inner product of U3 comma V2 over norm of V2 square times V2. This is V3 comma V1. Leave V1 the same. Replace V3 with this expression. Replace V3 with this expression. Leave V1 the same. Next, find the second axiom of inner product. Distribute V1. If I distribute V1, I get U3 comma V1 minus the second term is inner product of U3 comma V1 over the norm of V1 square times V1 comma V1 minus the norm of inner product of V3 comma V2 over norm of V2 square times V2 comma V1. Distribute V1 to all three terms. I get this. Next, by the third axiom of inner product, I can put a scalar in front of the first vector. I get U3 comma V1 minus put a scalar. This is a scalar. Put it outside the inner product. I get inner product of U3 comma V1 over norm of V1 square. If I put it outside, what's left is V1 comma V1. Same thing here. Put a scalar. Leave V2 inside. Put a scalar. Put a scalar outside the inner product. I get U3 comma V2 over norm of V2 square. If I put it outside, what's left is V2 comma V1. Since we already know that V1 and V2 they are orthogonal, the inner product of V2 V1 is 0. What's left is inner product of U3 comma V1 minus here inner product of V1 comma V1 is norm of V1 square. I get inner product of U3 V1 over norm of V1 square times norm of V1 square minus 0. And here norm of V1 square can cancel. What's left is U3 comma V1 minus, since norm of V1 can cancel, what's left is also another inner product of U3 comma V1. Since they looks exactly the same, they can cancel. We get 0. Since the inner product of V3 V1 is 0, that means V3 is orthogonal to V1. Similarly, if I put V2 here, the inner product of V3 and V2, similarly, by doing the same procedure, by doing the same calculation, it also turned out 0. Hence, V3 is orthogonal to V2. So both V1, V2, they are orthogonal to V3. So by doing this procedure here, by doing this calculation here, both V1, V2 is orthogonal to V3. Similarly, if I construct V4 in this way, take V4 equal to U4 minus the orthogonal projection of U4 on V1 minus orthogonal projection of U4 on V2 minus orthogonal projection of U4 on V3, the resulting vector V4 is orthogonal to all V1, V2, V3. Next, if we continue and repeat the same procedures n times, then the orthogonal set from V1, V2 up to Vn will be obtained. So, continue, repeat the same procedures n times. Then a orthogonal set V1, V2 up to Vn will be obtained. Next, we try to verify that V1, V2 up to Vn, they cannot be zero vectors. Can V1 be zero? Can V1 be zero? Since V1 could be U1, and U1 is a basis vector, U1 cannot be zero. Since U1 is not zero, V1 is not zero. Since V1 equal to U1, and U1 is a basis vector, U1 cannot be zero. Since U1 cannot be zero, V1 cannot be zero. So V1 is not zero. How about V2? Can V2 be zero? How about V2? Can V2 be zero? Assume V2 is zero, then what's gonna happen? Assume V2 is zero, then we have zero here. That means U2 equal to this expression. If V2 is zero, I can bring this over. So I got U2 equal to this expression. Then U2 equal to inner product of U2 comma V1 over norm of V1 square times V1. We know that this is a scalar. This is a scalar. Let's call it scalar K1. And V1 is a sense U1. V1 is a sense U1. That means I can write U2 as the linear combination of U1. Since U1, U2, Un, they are basis vectors, they must be linearly independent. So we cannot write U2 as a linear combination of U1. That's impossible. That's a contradiction. Since U1, U2, they are basis vectors, they must be linearly independent. So we cannot write one vector as a linear combination of the other vectors. That's impossible. That's a contradiction. Once we find contradiction, it means assumption must be wrong. So V2 cannot be zero. How about V3? Can V3 be zero? How about V3? Can V3 be zero? Assume V3 is zero. What's gonna happen? Assume V3 is zero. What's gonna happen? If V3 is zero, I can bring this term over, this term over. I get U3 equal to these two terms. Then U3 equal to these two terms, which is U3 inner product of U3 comma V1 over norm of V1 square times V1 plus inner product of U3 comma V2 over norm of V2 square times V2. If V3 is zero, I bring these two terms over. Both of them become positive. So I get U3 equal to these two terms. Here, V1 is the sense U1. If I replace this V1 with U1, I write V2 as a linear combination of U1, U2. Therefore, both vectors V1, V2 can be written as linear combinations of U1, U2. Since both V1, V2 can be written as linear combinations of U1, U2, this entire expression here can be written as a linear combination of U1, U2. This entire expression can be written as a linear combinations of U1, U2. But U1, U2, U3 up to Un form a basis. They must be linearly independent. So we cannot write U3 as a linear combination of U1, U2. That's a contradiction. That's impossible. Since U1, U2 up to Un form a basis, they must be linearly independent. Since U1, U2 up to Un, they form a basis, they must be linearly independent. We cannot write U3 as a linear combination of U1, U2. That's a contradiction. If we find contradiction, that means the assumption must be wrong. V3 cannot be 0. V3 cannot be 0. This is wrong, so V3 cannot be 0. Similarly, we can show that V4 is not 0. V4 is not 0. Up to Vn, they are not zeros. Similarly, V4, V5 up to Vn, they cannot be 0. Since V1, V2, Vn, they are non-zero vectors, then by earlier theorem we know that V1, V2, Vn, they must be linearly independent. Since this is orthogonal set and the vectors are non-zeros, they must be linearly independent. By earlier theorem, they must be linearly independent. Since V1, V2, Vn is a linear independent set with m vectors, since V1, V2, Vn is a linear independent set with m vectors, and what's the dimension of V? What's the dimension of V? Since U1, U2, Un is a basis of V, dimension of V must be n. Since U1, U2, Un is a basis of V, dimension of V is n. Dimension is the number of vectors in a basis. So dimension of V is n. Then what? Since V1, V2, Vn is a linear independent set with m vectors, and dimension of V is n, then the set V1, V2, Vn must be a basis of V. Then it's a basis of V. Since V1, V2, Vn is a linear independent set with m vectors, and dimension of V is n, then this set V1, V2, Vn is a basis of V. Hence, this is a basis in the orthogonal set. It's called orthogonal basis. This is an orthogonal basis. Hence, V1, V2 up to Vn is an orthogonal basis. So V1, V2, Vn is an orthogonal basis in V. That's how we use Grand Schmidt process to construct an orthogonal basis in V. Next, how can we construct Ulcer normal basis in V? How can we construct Ulcer normal basis in V? In order to construct Ulcer normal basis in V, we try to normalize each vector in the basis. Next, if I let W1 equal to V1 over its norm, we try to normalize each vector in the basis. If I let W1 equal to V1 over its norm, then W1 is a unit vector. Let W2 equal to V2 over its norm, then W2 is a unit vector. Continue. Let Wn equal to Vn over norm of n. Then all these W's are unit vectors. Then the set W1, W2, Wn for an Ulcer normal basis in V. The set W1, W2, Wn for an Ulcer normal basis in V. So that's how we construct Ulcer normal basis of V based on arbitrary basis in V. That's how we construct Ulcer normal basis of V based on arbitrary basis in V. Next, let me show you an example. Let S equal to P1, P2, P3, P4. Let S be a basis in the real inner product space P3. Here, P3 is the set of all polynomials with degree less or equal to 3. P3 is the set of all polynomials with degree less or equal to 3, where P1, P2, P3, P4 are 4 polynomials. Construct Ulcer normal basis of P3 based on S. Based on S, we try to construct Ulcer normal basis of P3. So first of all, we need to use Green-Schmidt process to find orthogonal basis. Then we can normalize each vector in the basis to find an Ulcer normal basis. So let's first of all apply Green-Schmidt process. For Green-Schmidt process, first step, we set V1 equal to P1. If the basis is U1, U2, Un, first step we let V1 equal to U1. Here, since our basis is P1, P2, P3, P4, first step we let V1 equal to P1. That's first step. Second step, let V2 be P2 minus the inner product of P2 comma V1 over norm of V1 squared times V1. That's the projection of P2. That's an orthogonal projection of P2 on V1. That's an orthogonal projection of P2 on V1. Next, let's compute the inner product of P2 comma V1 and norm of V1 squared. Let's do the inner product first. What's the inner product of P2 comma V1? In an inner product space, if the inner product is not specified, we use the standard inner product in P3. In P3, if the inner product is not specified, we use the standard inner product in P3. The standard inner product in P3 says, if f is f of x equal to a0 plus a1x plus a2x squared plus a3x cubed, and g is g of x equal to b0 plus b1x plus b2x squared plus b3x cubed. Here, f and g, they are vectors in P3. The standard inner product in P3 is, inner product of f comma g is the product of the corresponding coefficients, the sum of the product of the corresponding coefficients. We first of all multiply the corresponding coefficients and then add them up. We get a0 times b0 plus A1 times D1 plus A2 times D2 plus A3 times B3. We multiply the corresponding coefficients first, and then add them up. That's called a standard inner product in P3. In general, that's the standard inner product in Pn. That's the standard inner product in Pn. Let's apply the standard inner product here. Here, P2 is a polynomial, s squared plus 2x plus 1. V1 is the same as P1. Here, P1 is s plus 1. Then apply the standard inner product in P3. We multiply the corresponding coefficients and then add them up. We get 1 times 0 plus 2 times 1 plus 1 times 1. 2 times 1 is 2. 1 times 1 is 1. Altogether, we get 3. That's the inner product P2 comma V1. Next, let's find the norm of V squared, norm of V1 squared. Norm of V1 squared is the inner product of V1 comma V1. Here, V1 is the same as P1. So you get s plus 1 comma s plus 1. Then find the standard inner product in Pn. We multiply the corresponding components, multiply the corresponding coefficients, and then add them up. 1 times 1 is 1, plus another 1 times 1. We get 2. That's the norm of V1 squared. Then plug in. V2 is P2 minus this. P2 is this. S squared plus 2x plus 1 minus inner product of P2 comma V1. It's 3 over norm of V1 squared, which is 2, times V1. V1 is the same as P1. That's s plus 1. Then simplify. We get s squared plus 2x plus 1 minus 3 over 2x minus 3 over 2. Then combine like terms. We get s squared minus 2x minus 3 over 2x is half of x. 1 minus 3 over 2 is negative 1 over 2. That's V2. That's V2. Next, let's find V3. V3 is P3 minus inner product of P3 comma V1 over norm of V1 squared times V1. That's the orthogonal projection of P3 on V1. Next, minus inner product of P3 comma V2 over norm of V2 squared times V2. That's an orthogonal projection of P3 on V2. Next, let's compute inner product of P3 comma V1 and the inner product of P3 comma V2 and the norm of V1 V2. Let's find the inner product of P3 comma V1 first. Here, P3 is a polynomial s cubed plus 2s squared plus 1. That's P3. V1 is the same as P1, which is s plus 1. Then apply the standard inner product in P3. We multiply the corresponding coefficients and then add them up. We get 1 times 0 plus 2 times 0 plus 1 times 1 plus 0 times 1. Multiply, add them up. We get 0, 0, 1, 0, which is 1. So inner product of P3 comma V1 is 1. Next, let's find inner product of P3 comma V2. P3 is s cubed plus 2s squared plus x. v2 is this vector is v2. S squared minus half of x minus half. It should be plus half. It should be plus half here. Then apply the standard inner product. We multiply the corresponding coefficients. We get 1 times 0 plus 2 times 1 plus 1 times half plus 0 times negative half. Altogether, that's 0, that's 0. We have 2 plus a half, which is 5/2. That's the inner product of P3, V2. Next, find the norm of V1 squared and norm of V2 squared. We know norm of V1 squared is 2. Next, find norm of V2 squared. We know that norm of V2 squared is the inner product of V2, V2. And we know that V2 is this vector. S squared plus half of x minus half, comma S squared plus half of x minus half. Then apply the standard inner product in P3. We multiply the corresponding coefficients and then add them up. We get 1 times 1 plus half times half plus negative half times negative half. That's 1 plus a quarter plus a quarter. Quarter plus quarter is half. 1 plus half is 3/2. That's norm V2 squared. Next, compute V3. V3 is P3 minus this expression. P3 is s cubed plus 2s squared plus x. That's P3 minus the inner product of P3, V1, which is 1, over norm of V1 squared, which is 2, times V1. V1 is a sense P1, which is s plus 1, minus inner product of P3, V2. Inner product of P3, V2 is 5/2. Over norm of V2 squared. Norm of V2 squared is 3/2. Times V2. V2 is here. S squared plus half of x minus half. Then simplify. 5/2 over 3/2. If we simplify, that's 5/3. Multiply top and bottom by 2, we get 5/3. So V3 can be written as s cubed plus 2s squared plus x. If I distribute negative 1/2, I get negative half x minus half. If we simplify this, that's 5/3. Distribute 5/3, we get negative 5/3 s squared minus half times 5/3, that's 5/6 times x. 5/3 times half, that's 5/6. Double negative is positive. Then combine like terms. I get s cubed 2s squared minus 5/3 s squared That's 1 over 3x squared. X minus half of x is half of x. Half of x minus 5 over 6x. That's negative 1 over 3x. Next, the constant, negative half plus 5 over 3. That's 1 over 3. That's V3. Next, let's find V4. V4 is P4 minus inner product of P4 comma V1 over norm of V1 squared times V1. That's the orthogonal projection of P4 on V1 minus inner product of P4 comma V2 over norm of V2 squared times V2. That's the orthogonal projection of P4 on V2 minus inner product of P4 comma V3 over norm of V3 squared times V3. That's the orthogonal projection of P4 on V3. Next, let's compute the inner product of P4 comma V1, P4 comma V2, and P4 comma V3, and compute the norm of V1 squared, V2 squared, and V3 squared. Let's compute the inner product first. Inner product of P4 comma V1. P4 is a polynomial s cubed minus 1. V1 is a sense P1, which is x plus 1. That's P1, that's V1. Then compute the standard inner product in P3. We multiply the corresponding coefficients and then add it up. We get 1 times 0 plus 0 times 1 plus negative 1 times 1. There's no x cubed, so its coefficient is 0. There's no x here, so its coefficient is 0. The constant coefficient is negative 1 times 1. Altogether, I get 0 plus negative 1, which is negative 1. That's the inner product of P4 comma V1. Next, let's find the inner product of P4 comma V2. P4 is this s cubed minus 1. V2 is this s squared plus half of x minus half. Then compute the standard inner product in P3. We multiply the corresponding coefficients and add it up. We get 1 times 0 plus 0 times 1 plus 0 times half plus negative 1 times negative half. That's 0 plus 0 plus 0 plus half, which is positive half. That's the inner product of P4 comma V2. Next, compute the inner product of P4 comma V3. P4 is a polynomial s cubed minus 1. V3 is this. This is V3. We get s cubed plus 1/3 of s squared minus 1/3 of x plus 1/3. Then apply the standard inner product in P3. We multiply the corresponding coefficients and add them up. For x3, for s cubed, the coefficient is 1 times 1. For s squared, the coefficient is 0 times 1/3. For x, the coefficient is 0 times negative 1/3. And for the constant, the coefficient is negative 1 times 1/3. Altogether, we get 1 plus 0 plus 0 minus 1/3. 1 minus 1/3 is 2/3. That's the inner product of P4 comma V3. Next, compute the norm of V1 square, V2 square, V3 square. We know the norm of V1 square, that's 2. We know the norm of V2 square, that's 3/2. Next, compute the norm of V3 square. The norm of V3 square is the inner product of V3 comma V3. V3 is this vector. So we get the inner product of s cubed plus 1/3 of s squared minus 1/3 of x plus 1/3 comma s cubed plus 1/3 of s squared minus 1/3 of x plus 1/3. Then apply the standard inner product in P3. We multiply the corresponding coefficients and then add them up. We get 1 times 1 plus 1/3 times 1/3 plus negative 1/3 times negative 1/3 plus 1/3 times 1/3. One times 1 is 1. 1/3 times 1/3 is 1/9. Negative 1/3 times negative 1/3 is positive 1/9. 1/3 times 1/3 is 1/9. 1/9 plus 1/9 plus 1/9 altogether is 3/9. 3/9 is 1/3. 1 plus 1/3 is 4/3. That's the norm V3 square. Next, compute V4. V4 is P4 minus this expression here. P4 is s cubed minus 1. Minus inner product of P4 comma V1, that's negative 1, over norm of V1 squared, which is 2. So minus negative 1 over 2 times V1. V1 is the same as P1, which is s plus 1. Next term, minus inner product of P4 comma V2 over norm of V2 squared. Inner product of P4 comma V2 is half. That's the numerator. Norm of V2 squared is 3/2. That's the denominator. So we get half over 3/2. Times V2. V2 is x squared plus half of x minus half. Minus inner product of P4 comma V3 over norm of V3 squared. Inner product of P4 comma V3 is 2/3. Norm of V3 squared is 4/3. That's the numerator, that's the denominator. So we get 2/3 over 4/3. Times V3. V3 is this vector here. S cubed plus 1/3 of s squared minus 1/3 of x plus 1/3. Then simplify. We get s cubed minus 1 plus half of x plus 1. Half over 3/2, I can multiply top and bottom by 2. I get 1/3. 1/3 of s squared plus half of x minus half. here. For 2/3 over 4/3, I can multiply top and bottom by 3. I get 2 over 4, which is half. Half of s cubed plus 1/3 of s squared minus 1/3 of x plus 1/3. Next, distribute and combine like terms. We get s cubed minus 1 plus half of x plus half minus 1/3 of s squared minus 1/6 of x plus 1/6 minus half of s cubed minus 1/6 of s squared plus 1/6 of x minus 1/6. Then combine like terms. S cubed minus half of s cubed is half of s cubed. Next, negative 1/3 of s squared minus 1/6 of s squared is half of s squared. It's negative half of s squared. They are both negative. Half of x minus 1/6 of x is 1/3 of x. 1/3 of x plus 1/6 of x is 1/2 of x. Here, 1/6 of x cancel. What's left is half of x. And similarly here, 1/6 cancels negative 1/6. What's left is negative 1 plus half, which is negative half. That's V4. So V1, V2, V3, V4 together form an orthogonal basis in P3. So orthogonal basis is V1, V2, V3, V4. V1 is a sense P1, which is S plus 1. V2 is this vector, s squared plus half of x minus half. V3 is this vector, s cubed plus 1/3 of x squared minus 1/3 of x plus 1/3. That's V3. V4 is this vector, half of s cubed minus half of s squared plus half of x minus half. This is the orthogonal basis in P3. Next, we try to find orthonormal basis in P3. So we try to normalize each vectors in the orthogonal basis. We try to normalize V1, V2, V3, V4. And let's find norm of V1, V2, V3, V4. Since we know that norm of V1 squared is 2, so norm of V1 is square root of 2. We know that norm of V2 is 3/2. Norm of V2 squared is 3/2. So for norm of V2, we take square root. We get square root of 3/2. That's norm of V2. For norm of V3, we know that norm of V3 squared is 4/3. So for norm of V3, take square root. We get square root of 4/3. that can be rewritten as 2 over square root of 3. That's norm of V3. Next, for norm of V4, since we don't know norm of V4, let's compute norm of V4 square first, then take square root. Norm of V4 square is inner product of V4 comma V4. Here V4 is this polynomial. Half of s cubed minus half of s squared plus half of x minus half, comma half of s cubed minus half of s squared plus half of x minus half. Then apply the standard inner product in P3. We multiply the corresponding coefficients and then add them up. We get half times half plus negative half times negative half plus half times half plus negative half times negative half. Half times half is a quarter. Negative half times negative half, that's another quarter. Half times half is a quarter. Negative half times negative half is also a quarter. A quarter plus a quarter plus a quarter plus a quarter is 1. That's norm of V4 squared. So for norm of V4, take square root. Square root of 1 is 1. That's the norm of V1, V2, V3, V4. Next, normalize each vector. I take V1 over norm of V1. That can be rewritten as 1 over norm of V1 times V1. Then plug in. We know that norm of V1 is square root of 2. We get 1 over square root of 2 times V1. V1 is x plus 1. If we multiply, it can be written as 1 over square root of 2 times x plus 1 over square root of 2. That's the first vector. Let me call this vector W1. Let me call this vector W1. Next, W2 is norm of V2. It's V2 divided by norm of V2. That can be rewritten as 1 over norm of V2 times V2. We know that norm of V2 is square root of 3 over 2. Plug in, we get 1 over square root of 3 over 2 times V2. V2 is s squared plus half of x minus half. Simplify. 1 over a fraction is a reciprocal. That's square root of 2 over 3 times s squared plus half of x minus half. Then distribute. We get square root of 2 over 3 x squared. Distribute. We get square root of 2 over 3 times half x minus square root of 2 over 3 times half. If we simplify, it can be rewritten as square root of 2 over 3 x squared. If we simplify, 1 over 2 can be written as square root of 1 over 4. If we simplify, that's square root of 1 over 6 times x. Similarly, 1 over 2 can be written as square root of 1 over 4. If we simplify, that's square root of 1 over 6. That's W2. W3 can be written as V3 over norm of V3. That can be rewritten as 1 over norm of V3 times V3. We know that norm of V3 is 2 over square root of 3. So you get 1 over 2 over square root of 3 times v3. v3 is this polynomial, s cubed plus 1/3 of s squared minus 1/3 of x plus 1/3. It's s cubed plus 1/3 of s squared minus 1/3 of x plus 1/3. Then simplify. 1 over a fraction is a reciprocal. We get square root of 3 over 2 times s cubed plus 1/3 of s squared minus 1/3 of x plus 1/3. Distribute, we get square root of 3 over 2 times s cubed plus square root of 3 over 2 times 1/3 of s squared minus square root of 3 over 2 times 1/3 of x plus square root of 3 over 2 times 1/3. If we simplify, the answer can be rewritten as square root of 3 over 2 s cubed. Cancel square root of 3 from top and bottom. I get 1 over 2 square root of 3. 1 over 2 square root of 3 x squared minus 1 over 2 square root of 3 times x plus 1 over 2 square root of 3. That's v3. Next, for v4, for w3, for w4, we take v4 divided by norm of v4. That can be rewritten as 1 over norm of v4 times v4. We know that norm of v4 is 1. We get 1 over 1 times v4. v4 is this vector, is this polynomial. Half of s cubed minus half of s squared plus half of x minus half. 1 over 1 is 1. If I distribute 1, it stays the same. If I distribute 1 here, it stays the same. So w4 is half of s cubed minus half of s squared plus half of x minus half. So w1, w2, w3, w4 form an orthonormal basis in P3. So orthonormal basis in P3 here is w1 equal to 1 over radical 2x plus 1 over radical 2. w2 equal to radical 2 over 3 x squared plus radical 1 over 6x minus radical 1 over 6. w3 is this. Radical 3 over 2 x cubed plus 1 over 2 radical 3 x squared minus 1 over 2 radical 3x plus 1 over 2 radical 3. That's w3. w4 is this. Half of s cubed minus half of s squared plus half of x minus half. This is an orthonormal basis construct from this arbitrary basis S.